Organizers for allowing me to speak. In fact, this talk and the next one you can sort of think of as one talk. We go straight from one to the other, and that's feel free to interrupt with questions if you have. I'm interested in exact inhomogeneous solutions of Einstein's field equations. Out of all the different ways of looking at structure in the universe, there are several of them, and this is one of those that focuses on exact solutions, so fully relativistic, fully nonlinear. And each of these methods of studying has its own advantages. But in this project, what I'm interested in doing is taking an inhomogeneous model of, in principle, arbitrary inhomogeneity, but of known metric, and then calculating a general framework for a variety of cosmological observations, how to calculate them. This obviously is going to involve integrating down the past null code for an arbitrary observer at an arbitrary position in an arbitrary space-time, in principle. And then we would need to set up a whole structure for doing the calculation, and this involves propagating a set of coordinates from the observer down the light cone by lead dragging, and then working with the null geodesic equation and the geodesic deviation equation to extend how measurements would work at different distances. And using that, we then want to calculate things like the redshift, the proper motions, the diameter distance, image distortion, and so on. And this is work still underway. But our main application is to the Szekeres inhomogeneous model, which Tony's going to tell you about. Very interesting model. There's lots of possibilities there, lots of options, lots of inhomogeneity that you can explore. Okay. So in general, the idea is to generate for a given model and a given observer what we would expect for the observations, and then be able to compare that with real observations and therefore work on model construction or improvement. But it also allows us to explore what observations would look like in different kinds of geometry and topology. And Szekeres allows us more than the usual sort of thing. And as I mentioned, this is an exact solution method. It has its own domain of validity and is a complement to other ones where the variation is strong, where the light speed is finite, and so on, which other methods often don't use. So we complement and check methods with each other where they overlap. In the future, what I might hope to do is the inverse. Given a set of observations, try and determine what the space-time metric is from those observations. We've already been looking at that for spherically symmetric models for some time. But trying to go beyond that is a much, much bigger challenge. But if we were to do that, we would need to be able to generate models for which we knew the correct answer in order to test them. So what I'm doing now is a step towards that as well. I'm sure you've seen these lovely pictures that come out of local universe flow analysis. So proper motions and flows are very topical subject at the moment, and so the local group of galaxies, including the Milky Way, has been given this lovely name Laniakea. I hope I'm saying it right. And they've been trying to map the flows, Brentali and company, and they're Laniakea and the nearest cluster. So I'm very much interested in this as one of the observations, and in fact kind of focusing on that in this talk, on various scales, local universe and possibly bigger as well. So how do we do this? The observations that one might think about include obviously the redshift, the luminosity, diameter, area, distance, the number density of sources, the proper motions, that is the angular changing position on the sky. Currently not really possible all that far away, but I imagine that this will improve with time, as does everything. And also image distortions, which of course is basically lensing. One of the primary problems when you want to work with models that are not nice and strictly symmetric is that your sources move around. And so if you're trying to take your pass null cone, trace your light rays back, and you hit a source, and then you want to know what that source is doing, well, if the source is moving, how do you find the same source at a later time? Okay, so here's our light ray at some initial time, and at some later time the source is moved, and we want to try and track that, what is the angular position of that source at a later time. So the problem of just finding the light rays to track sources is significant, and potentially very burdensome. You'd have to maybe try multiple rays before you get close, a kind of a shooting method. But what I'm going to propose is a method that helps you avoid this. So basically, summarizing what I just said, if you just use trial and error, it's inefficient, but if we use the deviation equation, that can actually give us the angular motion, that is the proper motion on the sky of the source instantaneously, which allows us now to estimate the correct position to shoot our ray in. So that's something that becomes more important in future work, but I think the method is particularly important. So of course we start off with a particular observer. Sorry, pressing the wrong button. Observer and light rays coming in, and we need a set of coordinates. So obviously we set our standard coordinates of the observer, and then what we're going to do is essentially propagate those observers along the light observer coordinates along the light rays. So we're going to set this up. We obviously, if we have a given metric, then the metric has coordinates. We're going to set up an orthonormal basis near the observer, then a spherical basis, and then turn it into a null spherical basis, and finally propagate it down the null cone. And that's what the following slides summarize. So, if we're given a metric, then we will have a metric in terms of certain coordinates, and we choose a position for the observer. And then we set up some orthonormal basis, some reference frame at the observer. So there'll be 4 of those basis vectors. We convert to a spherical basis in the usual way. So the tilde basis vectors are in terms of the orthonormal basis vectors with overbars. And then we convert to null basis, a null coordinate basis, locally at the observer like this. The transformation is inverse, so this is the hat, the null basis in terms of the orthonormal basis and the reverse. And so we get this transformations, and these things then are the constants that define our past null spherical basis, and these are what we're going to propagate. And our scheme is that we go down each light ray, we generate an affine distance down each light ray, and we define the observer's angles theta and phi to be constant along each light ray. Right? That is necessarily lead dragging, and so we lead drag everything else as well. And that setup is exactly the same we need to use the geodesic deviation equation. So here's a kind of picture of our setup. Here's the observer's world line, and that's us now. Here's some emitter with its world line. So that's the emitter at some emission point. The light rays come from the emitter and arrive at us. If there is some width or extension at the emitter, then another ray would come here. But what we actually do is, in the vicinity of the observer, we set up this orthonormal base, this past null basis, which includes a vector down, back down the past null cone, an angular vector, and of course we can't plot theta and phi on this diagram, and then a time vector. So this would be observation at a later time up here. And what we're doing is we're propagating these as geodesic deviation vectors down the past null cone to here. Okay, so we're going to get the propagated basis vectors at each point down the past null cone. So now, in order to actually do the numerical integration, we start by finding the paths, that is the geodesic equation for null geodesic equation. And that's the equation that's good for tensor calculation. If you want to actually do numerics, then you need a total derivative, not an absolute derivative. And so you're calculating this thing, which doesn't look quite so tidy. You have to do the same thing for the null geodesic equation, for the geodesic deviation equation. That's the form that you get in all the textbooks. Second absolute derivative of your deviation vector with respect to affine parameter involves the curvature and the null vector, the geodesic vector, and your deviation vector. You have to convert that into a form that's good for numerics. Second total derivative, and it looks a bit messier, involving the Christoffel symbols and their derivatives, as well as first derivative of the deviation vector and the null vector. Okay. That then gives us a set of differential equations which we integrate in parallel. And we then get a propagated coordinate system. It is a coordinate basis, which is useful. And therefore we can transform between the local metric, the metric, given metric in the vicinity of an emitter, and the propagated basis. However, it turns out that actually, it turns out that although this is the thing that we've been propagating, it turns out we need the inverse basis vector to do many of the calculation. That's just the matrix inverse problem. We need initial conditions, and I've summarized them here, but essentially for the initial condition of the geodesic equation, we basically need to define what k is near the observer in the orthonormal frame, and this gives us initial condition like this. And similarly for the deviation equation, we say the time vector is the local flow for velocity, and then we take the chi-0 limits of the basis near the observer, and we get these things, and we use essentially the commutation of the coordinate basis in order to get initial conditions on our rate of change of the basis vector. Okay. So what we do is that at some initial time we have a basis, and then at some later time, to propagate that basis to later times, we have to use Fermi derivative is 0. Okay, so we Fermi propagate because the observer may or may not be geodesic. If it's geodesic, then it's simple parallel propagation. Okay, now we come to observations that we can get out of this. All right. Now, this way. There we go. So, the rate of change of your observer orthonormal frame coordinate. So this is your observer's basis with respect to observer time. We expand that with the chain rule in terms of the hat basis vectors. And so we get basically these components of the propagated basis and this quantity, which here we expand again in terms of chain rule, and we get contraction of the basis vectors with the, now this is the local flow pore velocity at the emitter, and then we identify one of these terms, this one, as one of the redshift. This is the rate of change of proper time at the emitter with respect to the proper time essentially at the observer. So this is your, this is that quantity, and just as a reminder, this is the source proper time, emitter's proper time, source proper time, observer's proper time, and T hat is the extension down the Pascal curve of the observer's proper time. Okay. Using that then, firstly, we've got a set of equations there. We use this, must be equal to unity at the observer. So from this, we can actually get the redshift in terms of that quantity, in terms of the propagated basis and the local flow, the local pore velocity. And then, once we've got that, we can get the rate of change of the observer's theta and phi with respect to the observer's time in terms of this quantity, the theta and phi basis, inverse basis vectors at the emitter and the redshift that we've got up here. And as I mentioned, it's the dual basis vector. And as I mentioned, it's the dual basis vectors that we need in order to do this, so we propagate in an invert. Once we have that, then, as I said, this allows us to track the sources because we know the instantaneous rate of change of angle on the sky for the observer. And that allows us to estimate, guess where to point the next ray. Another thing that we have to worry about, if the model is seriously inhomogeneous, is that the light rays and the constant chi, the constant affine parameter planes, or even the, may not be orthogonal, and we're interested in what's orthogonal to the line of sight. So what we actually see is projected onto the plane perpendicular to the line of sight. We need to find that viewing plane, which may not be the same as the constant z or constant affine parameter surfaces. So we need to basically define a spatial vector in the direction of the light ray. This is the local pore velocity. We define this to be orthogonal to that, and in the direction. So we figure that out. This is V, and then we project perpendicular to T, we project perpendicular to V, and that gives us this 2 surface here, which is the viewing plane. So this is the double the projection tensor. And as I mentioned, the actual extensions in space may not be perpendicular to the line of sight. So if we've propagated these basis vectors, they may or may not be perpendicular. This is something we're kind of continuing to worry about. But in terms of area distance, we would then need the physical area of basically of these two things. So we use the permutation pseudotensor, the T, the V, and these two displacements, which are essentially propagated basis vectors times angular changes. Right? And that's the angle subtended to the observer. This gives us the area distance. And the one thing that we're kind of still worrying about is how to properly account for the non-orthogonality that might be there. Just a small mention, since we're dealing with proper motions or flows, very roughly, the angular motion, the physical motion across the sky, is some kind of physical transverse velocity divided by pretty much an area distance or a diameter distance. As you know, the area distance has a maximum, which means that the angular size of objects has a minimum, and this means that the proper motion will also have a minimum, and beyond that, it will actually become more detectable. So that's something perhaps to look for, and now we go to the applications, the real hard work. Let me just summarize. Now, you can come out. We've developed an algorithm for calculating observational features for a given observer in a given model. This would facilitate exploring models and what they look like. We can try out interesting geometries. It gives us instantaneous angular flow rates, which would assist in tracking sources. And it's an important complement to various other ways of studying structure, which we're still refining. Thank you.
Hey, I'm just wondering, why is it important to actually identify the sources from time to time?
It's important to
track the sources, to identify that that distance that you measured before is the distance to the same object that you measured.
If you're interested in how things move and you want to do it over a longer period of time, then you're going to have to track it. Right? If you only want the current instantaneous flow rate, then this will do it for you. Okay. But as time goes by, we may be interested in tracking more than just that. Yeah. And in particular, when we're studying models, we have this possibility of analyzing how do things move.
This is beyond the optical properties, it's not...
It's beyond the instantaneous observational, yes. But since we're working with a given metric, we're saying what does it look like, we have this option of doing a time evolution of the observations.
Any other question?
Just a comment on that. I think maybe in a very futurist time, when we will be able to do some real-time cosmology with redshift drift and position drift, it might be a good test of dark energy and also maybe the isotropy probability. But this is, well, we are not yet at that point for observations.
Okay.